In section 3.2, we're going to continue our talk about graphing functions and see if we can identify four things about these two functions. We want to identify first, we want the function's domain, the range, the x-intercepts, and if there are any y-intercepts, we're going to talk about those too. And then we want to look at a couple of values just to see if we can identify what is the y value when x is -5 and what is the y value when x is 0, or f of -5 and f of 0. So for first, let's talk about A. Let's say we're going to look for the domain. Now the domain of this function is the x values. What's the possibility of x? Well, it can go all the way over to -infinity, and it can reach also as far as +infinity. So it's sort of an unlimited domain there. Let's talk about range. Well, look, it's going to stop right here, isn't it? It's going to stop at a y of -1. But how far down does it go? What's the smallest it can be? It could go all the way down to -infinity. And of course, as high as it gets, as great as it gets, is a -1. So that's the possible y values range. Now, the next thing they asked us for was any x-intercepts. This would be where it crossed the x-axis and it doesn't touch the x-axis. So we can say there are none. And for D, we're going to say any y-intercepts. And it looks like it's crossing right here, doesn't it? Where x is equal to 0 and y is -5. So that would be our y-intercept. Now, next question it asks is, what are the function values for f of -5? So when x is -5, basically what it's saying, when x is -5, what is the value for y? That's the part they're asking you. So I go to where x is -5 and I go down to y, and it looks like it's right here. X would be -5, and at that point y is a -2. Let's do the last one they asked for. When we have a function of 0, what is it? Well, when x is 0, what is y? And I see that it crosses. It's right there at the y-intercept, isn't it? So those are the questions answered for me. Now, that's a pretty common graph. It's not too hard to figure out. This one's a little different because you can see it's just a piece of a puzzle. It's just a limited graph. It stops. It stops right here where x is 4, doesn't it? In fact, it stops right above it or before it. And it also stops right here where x is 0. So it's kind of limited. Let's see if we can answer the same questions for it. Talking about first, A was the function's domain. So as far left and right as it goes, it will reach an x of 0. And it does reach that 0 because this is a solid dot that's filled in. Now, how far right does it go? It looks like we're getting to an x of 4 here, but it does not include that 4, so we put a softer rounded bracket to show that that 4 is not included. It just goes all the way to 4. As far as the range, we're talking about how far up and down this thing goes. The smallest value, we always start with the smallest value it will reach, is a -9. And then you have to ask yourself, does it reach that -9? Yes, it's included because it's got that solid dot. How far up does it go? It goes up to a +7, but it never reaches it. It just stops right before it. Now we want to know, what are the x-intercepts? Next question. Where does it cross the x-axis? It's right here, where x is equal to 3. And of course, if it's an x-intercept, y has to be 0. And now the y-intercepts. Where does it cross the y-axis? Well, it actually touches the y-axis right here, and it is included as a solid dot. So we can say where x is 0 and where y is -9, that's going to be called our y-intercept for this one. It wants to look at one particular value, the function value of 2 when x is equal to 2. In other words, when x is equal to 2, what is the value for y? So I have to find where x is equal to 2 and then go down and see if I can get really close to where it is. To me, it's right in between. I would say it's right in here. And I'm going to kind of guess at that and say it really looks like it's on the halfway point. So I'm going to say it is a -4.5. Now, on the next page, another factor about functions that we kind of get familiar with is whether they are increasing, decreasing, or constant. So if a function is increasing, as this one, it looks like to me, I always think about it, it's going uphill. An increasing function is headed uphill. But what that means is as the value for x goes up, in other words, as it goes to the right, x is getting bigger, then the value for y also goes up. And so I sort of think about it as that. When it's decreasing, as the value for x goes up, the value for y is going to go down. And that's going to be my decreasing thoughts. And then as it's a constant function, we'd see, well, as x is going to increase, we'll just talk about how it goes straight up the number line, y stays the same. So it doesn't change at all. And those are increasing, decreasing, and constant functions that you kind of want to get just used to that terminology. Let's take a look at these graphs and see if we can identify intervals on which the function is increasing and intervals in which it is decreasing, and intervals maybe where it is constant. So those are our A's and B's and C's. So let's look at A, and we'll put it out here and say, are there any intervals in this particular graph where the function is increasing? Well, I believe it starts right about here, and it starts to swing upwards, doesn't it? This would be an increasing function. It would be after x was 1. In other words, where x was greater than 1. So I would say it's the value from x is equal to 1 to positive infinity, right? It will keep on being an increasing function. And B, where's my decreasing part of this function? Well, the opposite. It starts at x of 1, doesn't it? It goes from 1 all the way down. So I'm going to say it goes to negative infinity. And then it stops at 1. It stops decreasing here at 1. That's where it swings around and goes up. And I'll say kind of included both of those. And then the next thing it's going to ask us is, are there any intervals on which it is constant? Well, 1 doesn't count. And what we're saying is this looks like, and it should, just touch 1 and turn, even though it looks like it might stay on that level for a while. It really doesn't for this particular graph. So we say, no, there are no intervals where it is constant. For the second one, if I'm looking for increasing parts of the function, I'd say there really are none. This function doesn't increase at all. Decreasing, well, it starts about here, doesn't it? It starts where x is equal to 1, and it goes till x is a positive infinity. So that's my decreasing part. And is there any part of this function that is a constant? Right here, all the way from negative infinity to a value of 1 for x is where I would say it is a constant. This section really talks about something called relative extrema. And when we're dealing with that, we're dealing with a relative minimum and a relative maximum. Now, it's not the complete minimum and maximum of a graph. It's not as high as it ever goes or as low as it ever goes. But it is a low point or a high point based on the graph that is next to it, the part of the function that is next to it. So you can see in the illustrations, this dip down would have really a minimum relative to the rest of the graph that's around it. It would also have a maximum relative to the rest of the graph. So we would call this its relative maximum and its relative minimum. And we could identify those, based on how far down they went, how far down it was, or how far up it was, or its coordinates, okay? So now let's look at this particular illustration here. And we're going to look at the numbers at which this function has a relative maximum and find out what that relative maximum is, and the numbers at which it has a relative minimum, and see if we can see what that relative minimum is, okay? Now, between this one, I'm going to go for the relative minimum first because it's the first thing I see. And I'd say it has a relative minimum. And I would say it's right here at x is equal to 2 and again at x equals 4. So it's at x equals 2 and x equals 4. What is that relative minimum? Well, it looks like it is going to be 2, 1, and 4, 1. So I'm going to put those down. I've got a 2, 1, and a 4, 1, the relative minimums I'm seeing. And what is the relative maximum? This is it. The point right here it reaches. It's relative to the rest of the graph that's around us. This is definitely a high point. So it has a relative maximum at, and we'll say it's got a relative maximum at x equals 3. And that point would be 3, and it looks like it's going to be 5. Is my relative maximum for this one. And they're not usually too hard to identify unless you've got a really unusual graph. I want to show you what you can do with your calculator with relative minimum and relative maximum. So I've got my TI-84 here, and I want to look at a window. This is the window size that I'm talking about. The window has been set for this one to a negative 5, 5 by 1, negative 60, 60 by 1. Let's go and set our window size, because I don't think mine's set that way. So I'm going to say this one is a negative 5, and the high it's going to be is a 5. It's going to be in increments of 1. For y, I'm going to do something a little different. I'm going to do a negative 60, positive 60, and increments of 1. So it's going to be a little distorted, but it allows these peaks and valleys to actually show on the screen. And otherwise, if you tried it, it probably wouldn't. Next, let's go over to y equals, and let's enter this particular function. Now, it's complicated. We're going to say 2, and we're going to have an x here. And then we're going to say to the power of 3. I'm going to use this arrow up and say 3 here to get my exponent of 3 in there. And then I say minus, I don't know if you can see what I'm doing. Let me see if I can do that better. Minus 6 x again, and I'll square it this time. And then I have to say minus 18x, and then last part of it is plus 7. And then check it to see if I got it entered correctly. It should say 2x cubed minus 6x squared minus 18x plus 7. It looks right. So let's look and see what this looks like as a graph. And you see how I did have to put increments of, between 60. That's what all those little hash marks are so close together for. Is otherwise this thing would have been way off of my graph window, which is kind of limited. So I see there's a relative maximum, and I see there's a relative minimum, but I have no idea what they are at this point. So I'm going to go and do something else with it to see if I can find them and make it identify what they are. Now, the button you want to do this with is right here. It's the calc, the blue calc right above the trace button. So you're going to be hitting second and trace. I'm going to say second and trace, and that gives me calculate. And then you can see I have a minimum and I have a maximum here. Why don't I work with the maximum first? I'll go down here and say, whoops, that's not what I want. I'll go down here and say maximum. And then it says, it puts my cursor, if you want to call it that, right here blinking in the middle. And it goes down here and tells us, where's the left bound point? In other words, it says, put me left of the maximum. And so I take my arrows and I go left of that high point that I want. I just have to get to the left of it anywhere. And then I hit enter, and it sort of marks it. And then it tells me, okay, show me what's right of it. And I go to the right of it, just using the arrow key, and I hit enter again. And then it says, now, do you want me to guess what the highest point within that little range that I've marked off? You can see the little range has been marked off. You want me to guess what the highest point is? And I hit enter to say, yes, I do. And it tells me that it has an x value of negative 1.00000, okay? So at that point right here, this is, according to my calculator, negative 1, and it has a y of 17. It's really close to that. I mean, I know this is off a little bit usually. It's not completely on exactly, but it tells me really close. Negative 117 is the relative maximum, isn't it? Let's do the relative minimum. We're going to go back to this calc button, and this time we're going to choose minimum. And we have to move over to where we're getting close to the minimum. Okay, we just need to be before we get to the deepest part, and hit enter. It draws a little line, and we go a little further just past it, and we hit enter again, and now we hit enter again. And it gives us where our relative minimum is. Now, it's 2.99999. I'm going to call that 3, okay? I'm going to call that an x value of 3. And the y is a negative 47. Close enough. So you can see how your calculator can help you identify, even for a very complicated function like this one, can help you identify. You wouldn't want to have to graph this one on your own and try to find the relative minimum and relative maximum. Now, another feature of functions is consider their symmetry. And when we talk about their symmetry, we consider functions either even or odd based on some of their symmetry. So I've made a little chart for you here. Basically, if a function sorry, is symmetric with respect to the y-axis, in other words, you can see this one is, you could fold the y-axis, fold the piece of paper in the top on the y-axis, and it would perfectly overlay that function, wouldn't it? So it's symmetric with respect to the y-axis, and we call this one an even function. I think it's written over here for you too. So we have all even functions have this kind of symmetry. If it is symmetric with respect to the x-axis, well, this one is not a function, is it? Because you can do the line test and you can cross it in more than one place, can't you? So, but we call this one, it's symmetric with respect to that x-axis. If you fold it on the x-axis, you would see that it would overlay itself. It would be a perfect match. And then we say, is it symmetric in respect to the origin? So, I could fold this piece of paper diagonally right through the middle of the origin, and it would lay on top of itself perfectly. And so this one is considered an odd function because it has origin symmetry. Now, we can tell whether they have even or origin symmetry or y-axis, x-axis, or origin symmetry. We can tell by just doing a few simple steps. And I've replaced these problems at the bottom. I found some better examples that fit your My Open Math better. So we're going to use this page. You might want to stop your tape just a second and copy these down. And we're going to talk about, if you have to check for y-axis symmetry, which would be that even symmetry, what you do is you replace x in your function with negative x, and then you check to see if it is exactly the same thing. This one is supposed to say x squared. Hang on just a minute. Let me make sure I've got this right. That should say x squared instead of a squared. Hopefully you saw that before me. So I'm going to replace everywhere I see an x, I'm going to put a negative x. So this would say negative x, and because it is negative, I better put it in parentheses, minus y cubed is equal to 3. Well, a lot of these symmetry issues are going to deal with the exponents. If I square a negative, I have a positive, right? So that function does have y-axis symmetry, doesn't it? Because this is exactly the same as the original function. Let's check to see if it has x-axis symmetry. Instead of replacing x with negative x, this time I'm going to replace y with negative y. So I'm going to say x squared minus, and I would say negative y cubed is equal to 3. Well, x squared doesn't change, but this is negative times negative times negative, which is a negative, right? So it would be negative y cubed times a negative, which would cause it to be a positive y cubed. And hopefully you see that logic. We do this first. We end up with a negative y cubed, and then we say times a negative, came out positive. And of course, this is not the same as our original function. So we're going to have to say, no, it does not have x-axis symmetry. Let's check and see if it does satisfy the condition for both. We'll change both the x and the y, okay? So I'm going to say instead of x, I'm going to say negative x squared, and it would be minus a negative y cubed, and that's going to equal 3. Now, negative x squared is just plain old x squared. This one, we already found out, turns positive. 3 negatives multiplied together makes a negative, then times one more negative, I'm going to end up with a positive y cubed, and that's just 3. But when I look at the original function, it is not the same, so it doesn't have origin symmetry. It only has y-axis or even symmetry. Let's check out the second function that we have, and it says that for this one, I'm going to replace x with negative x. I'm going to say negative x is equal to y squared plus 19. Now, there's no simplification to be done there. You simply compare it, and you see that it does not match up. What if I replace y with negative y? Well, then x would equal a negative y squared plus 19. And that works for me because negative times negative is just going to give me that positive y squared again. And I'm good. I have x-axis symmetry. What about both? I'm going to plug it in and say negative x is equal to a negative y squared plus 19, and negative x equals y squared plus 19 does not give me the same as my original formula function. So nope, it does not. One more to try. X squared plus y squared is equal to 16. So for x, I'm going to plug in a negative x. And I have negative x squared plus y squared equals 16, which would give me just plain old x squared plus y squared equals 16, and I'm good. It has y-axis symmetry. When I substitute negative y for y, I get x squared plus negative y squared equals 16. And I get x squared, once again, negative times negative gives me that positive y squared equals 16. And yes, it does have x-axis symmetry. So as you can guess, the both is going to also work for me. I'm going to say negative x squared plus negative y, and then I square it, equals 16. And this becomes positive x squared, and this becomes positive y squared, and that's 16, and it does also have origin symmetry. So let's just put all this together. We're going to look at this graph and see if we can just say, okay, we know it's an unusual graph. Can you identify the domain of x? The domain, how far to the left does it go? It goes all the way to negative infinity. And how far to the right? Well, if it keeps on going, even slanted out that way, eventually positive infinity. So that's my domain. What about the range, which we know is up and down? Well, I look for the smallest value first, and it looks like it's going to hit negative 1. I'm going to say it reaches that negative 1. I believe it does. And then it goes all the way up to a positive 8. It looks like it does reach that value too. So negative 1 to positive 8, that's where it's contained within the range. Or is it? Now look, I just looked again at my graph. This thing is going to go a range. It's going to keep on going, isn't it? So it's not going to stop at 8, is it? It's going to go all the way to positive infinity. So it would be from a negative 1 all the way to positive infinity is going to be my range. What about x-intercepts? Now, where does this thing intercept the x-axis? It looks like 2 points where it crosses it. This is an x value of 2, which would be the 0.20, because y has to be 0, right? And again, where x is equal to 4. What about y-intercepts? Well, it looks like it's going to do hit right here, isn't it? Where x is 0, but y is 8. Next, on the intervals on which f is increasing, where is the function increasing? Well, when it stops right here from x is equal to 3, and then all the way to x of positive infinity, right? So I'd say it starts increasing. It starts at 3 and goes to infinity. That's my x values for the increase of this function. What about decreasing? Well, okay, it's going to start decreasing here, isn't it? And all the way down to this point. So I'd say I start decreasing right about where x is 0, right? I could say it starts there. Really, it's not really too picky about whether it is on that point or not. And then it stops decreasing maybe where x is equal to 3. And you could use either brackets for those. It's probably not going to be very selective about that. Intervals on which f is constant. Well, the constant function is right here. All the way from negative infinity to an x value of 0. And yeah, we'd say that's constant part of it too. Now, where does it have a relative minimum? Well, I think this would be my relative minimum, where x is equal to 3 and y is equal to negative 1. It's going to be my relative minimum. and the number at which it has, and the relative minimum would be 3, -1. You could say x is equal to 3 for that one, and the relative minimum is going to be 3, -1, or y is equal to -1. I'll write it just a different way. Now, what is the value? What is the point which is considered the function of -5? In other words, when x is -5, what is y? I know I'm going to have -5 as x. What is y when x is a -5? Well, I go out here to see -5 and go up here and I find, yeah, it's going to be during that constant part of the function. So it's going to be a y of 8. And then I look for the function of x is equal to 3. In other words, what it's saying is this time, what is x when y is equal to 3? You can interpret that as y is equal to 3. Well, when y is equal to 3, what have I got for x? And I come over here and I find this point right here. X is going to be 1. You could write that as a point if you wanted to. Now, is it even, odd, or neither? Do you see any type of symmetry in this graph? And I would think you would see this very clearly, that it doesn't have any symmetry. It doesn't have y-axis symmetry. It doesn't have x-axis. It doesn't have origin symmetry. I can't fold this graph in any direction and get it to duplicate itself. Now, another thing we can consider, or we can talk about, is something called piecewise functions. And piecewise functions are really two separate functions, and they have separate values depending on what x is. In other words, the function of x is 4x plus 4 when x is less than 0. But if x is greater than or equal to 0, the function is going to be 4x plus 7. You can tell these are linear equations. It would be like y is equal to mx plus b in both of them. So they're straight lines. I know they're straight lines, but it's going to be a different line when x is less than 0 than it is when x is greater than or equal to 0. And I've got 3 points for us to consider. I'd really like us to consider a fourth one. I want to look at the f of -1, function of -1 as well, okay? Now, let's say I have function of -3. All I have to do is say, where is it? Which one of these do I use if x is -3? Well, that's less than 0. So I'm going to say that's equal to 4 times -3, and I'm using the first one, plus 4, right? Which is going to be -12 plus 4, which gives me a -8. So I could plot that point. I could say I have an x of -3, and when I have x -3, y is -8. So I'm going to go down here and say there's my first point for that one. Let's do another one. Let's do when x is 0. What is y when x is 0? Well, it's not going to fit in this one because that has to be less than 0. So it's going to go up to the next function that I have. And I'm going to have to say that's going to be 4 times 0 plus 7, which is just going to be 7. So it would be 0, 7 is one of the points on that second part of the function, isn't it? Well, let's do another one. It's when x is 1, f of 1, right? So let's see if I have x of 1. I'm going to use this one where it's greater than or equal to 0. So I say 4 times 1 plus 7 is equal to 4 plus 7, or 11. And I'll plot that point. It's 1, 11. So I know it's a straight line. So I know this line is going to start here at x, where x is 0. And it's going to include that 0. So I circled it in, okay? Because I know it includes that 0. Because it says greater than or equal to 0, right? So I'm going to draw a line as well as I can that says that's my part of the function that is 4x plus 7, okay? It stops, but it stops right here. What about the rest of it? Well, I only ended up with 1 point on it. That's why I said let's do another one. Let's do where x is -1. And when x is -1, I've, of course, got to use this particular function. So I say 4 times -1 plus 4. And that's going to be it's going to be -4 plus 4. In other words, in this one, y is equal to 0, isn't it? So it's going to be on the x-axis. And what is it going to be? -1, 0. So it's really goes to here, doesn't it? So I can sort of say, okay, my line, this second line is, I know it's linear because I know the y is equal to mx plus b makes a straight line. This one does keep going until it gets to my, and I could, if I was really accurate and straight, I would know I was doing it right. I'm going to guess. But it does not include, I'm going to put an open circle there because that point is not included. So this is a piecewise function. Now you can look at it a different way. We can try to put this in the graphing calculator, and I'd like for you to try this anyway. Let me clear some stuff. And I'm going to hit quit there. And I'm going to go back to plotting these, and I've been y is equal to, I'm just going to clear that one. I'm actually going to enter both of these functions. I'm going to say y is equal to 4x plus 4. And then I'm going to go down to the next one and say y is also equal to 4x plus 7. Now, I don't know if you remember what window we left this thing at, but it was an awful window for graphing most anything. So I'm going to go change my window settings to, and I like to use this a lot, -10 to +10, increments of 1. Let's fix this one to -10 to +10 with increments of 1. And now let's go graph right here and see what it does. Now, it graphs the first one you entered, which was this 4x plus 4, with the blue line, and then it graphs the second one I entered, is that right, with the red line. I believe that's the way I entered them. It's graphing them like that. So you can see that these functions are, two different lines, but I know that one of them, I can get rid of this part where it starts below, below 0, right? The red line, from here all the way down, I can get rid of it because it's not included because x would be smaller than 0. This one would not be included, the blue one would not be included where x is greater than 0. So you can see my piecewise function has the gap of about 3 in it, which is what I had. This blue line was the first one. It came to here. Then I went on the red line and went up. And I just have to dismiss the other two pieces of that graph that I know are not part of those piecewise functions. So your graphing calculator can kind of help you to see if you're on the right track here. This one gives us a chance to try it again. Piecewise function is very similar to what we just did. The function of x is x plus 1 when x is less than -4, x minus 1 when x is greater than or equal to -4. So we can plot some points in there, and we would just pick our points and see what we wanted to plot. And I think I would choose -4, which is going to be a part of this one. So I'm going to say the function where x is -4 is going to equal this bottom one, right? It's going to be -4 minus 1, which is a -5. So y is -5 when x is -4. That's one point. Is it something I should color in or open circle? And it's got the equal sign to it, so it is a part of that function. So let's go color that one in when I say -4, -5. See if I can find it here. And I'll put a solid dot because it's a part of this particular function. Now let's see another one. We want to go greater than -4. Why don't we do one like, let's do -2. That gives us -2 minus 1, and that's, of course, -3. So I've got the point that I'm going to plot is -2, -3. And I would come out here and say that's one right there. Now at this point I've got 2 points, and I could draw that part of the piecewise function. It's going to carry on as far as greater than -4, which is all the way to the right. So there's my first linear function. See if I can do this with something that's straight. That's one part. Let's go do another part. Let's try to plot some points, some values for x less than -4. So if x is less than -4, well, let's make it, it has to be like f of -5, right? And that's going to be up here, isn't it? So I'd say it's -5 plus 1, which would equal a -4. So that point would be x of -5, y of -4. And I get to -5, -4 right here, okay? It is included in there, isn't it? Because I didn't use -4. It would be, I would be able to go all the way up to the part where x is -4 and put an open circle here. But let's find another point on my line so that I can draw a straight line here. I'm going to say, how about function f of negative 8 might help me. I think I can get that one on here. It would be negative 8 plus 1, or negative 7. So that point is going to be negative 8, negative 7, negative 8, and negative 7 is right here. And now I can draw this part of the function, this line, it's going to go down, because it goes everything to the left. Now, where does it stop? Well, it stops right here. I'm going to draw a circle here. It goes all the way there, but it stops because that's where the other function, the other piece of it, takes over, isn't it? This one is x is greater than or equal to negative 4. This one, it has to be everything less than negative 4. So there's my two functions with that. And you could put these two linear equations inside your calculator, and you could see your calculator graph both the lines. And you would just have to say, okay, this is the part that I use for less than negative 4. This is the part I use for greater than negative 4. So if you go into higher levels of math, the bottom of this page is talking about something called the difference quotient of a function. And it's the way that we can look at the curve or the slope of a function. It can also find the slope of a straight line, but we usually do that with it's an easier formula for that because it's already in an mx, y is equal to mx plus b format for the linear equations. But if you have some more complicated functions, then you might want a difference quotient to see if you can find slope or curve, okay? So anyway, we're going to take and do a demonstration of how it works using this function. X squared is x squared plus 3x. Now, I've got your difference quotient, or your expression that we'll fill in, written up here. And we have, of course, x plus h. We'll take and add h to the value of x and plug it in and evaluate for that expression. And then we'll subtract the function of x, and then we'll divide by h. Let's just do this as an example. What I have to do first, though, is find the function of x plus h. So for every x in this equation, I'm going to plug in x plus h. So this is going to equal x plus h, and of course that would be squared. And then I would take 3 and multiply it times x plus h. When I do this one, it's going to turn out to be a perfect square trinomial, and I know the rules for that. I say square the first term, so that's x squared, multiply the two terms together, and then double them. So I'm saying x times h times 2, that would be 2xh, and then square the last term, so I'll have h squared. Now I want to distribute this 3, so I'll have 3 times x, and I'll have 3 times h. I would simplify this if I could, but there's no like terms, so there's nothing I can do with it. And I'll just keep it because it goes right in this first part of my expression. Now, it's really simple now. My expression should say the function of x plus h, which is x squared plus 2xh plus h squared plus 3x plus 3h. And then I'm going to subtract this function, the normal one, the one I had, x squared plus 3x. Well, if I subtract them, I'm going to have to turn both of those terms negative. Or you put it in parentheses and do that in a future step. So I'm going to distribute the negative now, and I'll say negative times x squared is a negative x squared. Negative times 3x is minus 3x. I'm going to draw a line through this to show that I've replaced it with that part, those two terms. And then next thing I do is say I'll have to divide all of this by h. Now I'm starting to simplify. I'm going to start simplifying values. And I see that I have an x squared and a negative x squared, so I can cancel those out. I have a negative 3x, and over here I have a positive 3x. Those will cancel. So let's simplify it. Let's write it down and see what we have next. I have left over, it looks like I have 2xh plus h squared plus 3h. That's everything in the numerator, and I'm going to divide that by h. Well, each of these terms in the numerator has an h in them, so I can do that division. When I divide 2xh by h, I just end up with 2x. H squared divided by h just gives me h, and 3h divided by h gives me 3. So the difference quotient for this particular function is x squared plus h plus 3.